Alright, so let's go about section 8.3, trigonometric integration. So in this section, we are going to use mostly u substitutions and in some cases integration by parts on integrals that contain trigonometric expressions on their integrands. And in this case, we're going to use pretty much all the trigonometric identities, but most commonly the ones that are Pythagorean identity. But of course, other trigonometric identities come later. You'll see how that works. And well, so in this case, for this section, I have split it into 3 different topics or 4 different topics. I can remember the number exactly at this point. But the first one deals with powers of sine and cosine. Well, and whenever we have a power of cosine that is odd, what we need to do in this case is to save one cosine factor and then use this Pythagorean identity and then express the remaining factors in terms of sine. Alright, so that's what we do. That's the first thing we do. And well, for the power of sine, when that power of sine is odd, in this case not the cosine, we do pretty much the same, but in this case what we save, it's a power of sine, represent the remaining powers of sine as cosines, and then well, the idea is that our u will be that will be the cosine function. Well, of course, where are these 2 trigonometric identities coming from? Well, those come from sine theta squared plus cosine theta squared equals to 1. That's the Pythagorean identity. Yes?
Do we need to make cosine squared equals 1 plus sine?
1 plus sine. Which one?
The second one. Because it's sine square of theta and cosine square of theta.
Mm-hmm. So
is the cosine supposed to be plus cosine or plus sine?
This one is a minus.
At the bottom.
The bottom? This one?
Yeah.
Oh, the power reduction formula. Well, that one is minus and the other one is plus for this power reduction. So these 2 come from the Pythagorean identity, sine squared plus cosine squared equals 1. But keep in mind that these identities are true. For example, if I change, I don't know, maybe sine squared of 5x plus cosine squared of 5x equals to 1. As long as these 2 angles here are the same, they apply. Of course, we can use even something even crazier than this, like sine squared of e to the square root of x plus cosine squared e to the square root of x equal to 1. Yes, as long as both angles on the trigonometric identity, they are both the same. Alright? And it's important to keep in mind, so when we look at some examples for which the angle are not just x or just theta, that also is taken into account when we do the setup for the u du part of the problem. Alright, so the first 3 points are to discuss the odd powers of sine and cosine. But what happens when the powers here are even? Well, in this case, we need to use what I usually call the power reduction formula. So some textbooks call it the half angle. Other textbooks, I prefer to call them power reducing, because well, when we apply this formula, we reduce the power of sine, but we duplicate the angle. Right? So you'll see how this works. Of course, we're going to do examples of each. Okay? So let's have a look at a couple of examples. And what do we have? The integral of cosine cube of x over 3. Alright, so number 1. Let's identify the parity of the power of the trigonometric function. And in this case, well, we have a cosine with odd power. Alright, so so that means, so that's going to take us to the first part of the guidelines. Well, so we need to save 1 power of cosine and then use the trigonometric identity. So I'm going to rewrite the integral the following way. Cosine squared of x over 3 times cosine. Actually, I'm going to use a different color for a big purpose. Okay, so in this case, we will replace this cosine squared with 1 minus sine squared x over 3, and that times, I ran out of space here, no, should be sine, not cosine. Alright, so how is it going to work? The thing is that we have sine squared over here, which can very well work as the u, because what's the derivative of sine? Cosine. Don't we have that factor of cosine multiplying with the dx here? So this is great, because we can just call it u equals to sine x over 3 du, which is 1/3 cosine x over 3 dx, and well, cosine x over 3 on the other hand equals 1/3, oh actually not 1/3, it's 3 du, right? So when we do the substitution, this is going to look the following way. The integral of 1 minus u squared, and this whole thing, cosine x over 3, becomes a 3 du, for which we can take out the constant and integrate each term. Well, what's the integral of 1 with respect to u? U. And what's the integral of u squared? U cubed over 3 plus c. Distribute the 3, we get u, or 3u minus u cubed plus c, and all we do from here is back substitute for u. That's 3 sine x over 3 minus sine cubed x over 3 plus c. Alright? Again, like I mentioned before, most of these integrals are going to lead to basic u substitution, basic general power rule. But the real trick here, the real deal here, is to know how to manipulate these trigonometric identities in order to make this work with the u du part. Alright? Let's have a look at another example. Alright, so let's see, letter B. Sine to the 5th power of x plus times cosine squared x dx. Alright, what do we have in here? So in this case, whenever you have a combination of cosine, of odd powers and even powers, focus, let me write this note here, focus on the odd power. I know what you might be thinking. Well, yes, so we can also use the power reduction formula, but there is a problem with using the power reduction formula here, that in this case the problem is, well, 1 plus cosine 2x over 2. Well, in this case the problem with this is that we will have trigonometric functions with different angles, and in this case our purpose is to deal with functions having the same angle all the time. Okay, so that's why, and we get this done by just focusing on the odd power. Well, so this will be the integral of sine to the 4th power of x cosine squared x, and I'm gonna write the power I'm saving for the u du part with a different color. All right, and then from here we will manipulate the signs. Well, Why do we manipulate the sign? So we need to express all these signs right here in terms of cosines, because the part that stands the du, which is sine is the derivative of which function, by the way? Cosine or negative cosine. Well, the sign doesn't matter. So, and that what I'm trying to come up with is with the pattern recognition, right? And in this case, that what we need to recognize is that sine is the derivative of cosine. Well, negative sine rather. So that's why we want to have everything here in terms of cosines. All right. So let's see. Oops. To do that, I'm going to rewrite rather this sine to the 4 as a sine squared to the second power. And then from here, we will replace this sine squared using the Pythagorean identity. What's sine squared equal to? 1 minus cosine squared. Quantity squared. Cosine squared. X sine x dx. Alright? So, well, we need to write this in terms of a polynomial. Well, in this case, we need to expand the binomial in terms of cosine. Well, again, you can FOIL it if you want. That's fine. Write it as a product of this quantity and itself and FOIL it, or use the binomial formula, the binomial square formula, which I'm going to write over here. This one, I'm going to do a minus b, quantity squared, a squared minus 2ab, plus b squared. Okay, and then from here, okay, let me do the expansion. So 1 squared, which is 1 minus 2 cosine squared x, and what else? Cosine squared would be cosine to the 4th power times cosine squared x, and times the factor that stands the du part of the problem. Okay? So I think from here we're ready to do the use of, well, not yet. How about we distribute first this cosine times 1, cosine squared times cosine squared, cosine squared times cosine to the 4th. And then, so that's going to lead to the following result. That's the integral of cosine squared minus 2 cosine to the 4th plus cosine to the 6th. And that times sine x dx. And well, from here we can set up the du part. So when I first started the course, what I did is to distribute the sine x dx to every single term and then write 1, 2, 3, 4 integrals. That's not necessary because that's a little bit time consuming, and in this case, well, we have powers of cosine that can be then converted in terms of u, so that's fine. No need to do the distribution. So u equals to cosine x. What's the derivative of cosine? Negative sine, and sine dx, sine x dx rather, equals to negative du. So from here I'm going to replace this integral right here. So that's u squared minus 2u to the 4th and plus cosine, oh no, not cosine, plus u to the 6th times negative du. Be careful with this negative du, right? Now, before integrating, how about we use this negative sign to change the sign of these 3 terms inside of the parentheses. Okay, so that's going to be the integral of negative u squared plus 2u to the fourth minus u to the sixth du. And from here, we can just use the general power rule 3 times for one for every single term. All right? Let's see. So that'll be negative u to the third over 3 plus 2u to the fifth over 5 minus u to the seventh over 7 plus c. And that's pretty much the calculus part. From here we can just back substitute for what we said for u, which in this case is cosine. So that's negative cosine cube x over 3 plus 2/5 cosine to the fifth minus 1/7 cosine to the seventh plus c. And that's final answer. Any questions about anything we have done for this exercise? Let me zoom it out so you can see the whole problem in case you missed anything. All right. Okay, perfect. Ready for the next one? All right, let's have a look at the next exercise, which is sine to the fourth power cosine to the second power. Well, what do we have in this case? Half angle. Why is that half angle again? They're both even powers, right? So in this case, well, none of these are odd power, so in this case we're not going to save a power of, well, either sine of cosine, whichever has the odd power. No, in this case we will use power reduction or half angle. All right, so let's have a look at this one. Number one, the power reduction formula or half angle formula works when we have, well, preferably powers of 2. Power 2 for everything, for the trigonometric function. Well, in this case, well, notice we have a power 4. The first thing I would like to do first, before using the power reduction formula, is to rewrite that, because cosine squared is ready. It's pretty much ready to be transformed into its corresponding reduction. So I'm going to rewrite this as a sine squared times cosine squared x dx. All right, so from here, and this is equivalent to 1 minus cosine to x over 2, and this is equal to 1 plus cosine to x over 2, which is what I'm going to replace with in the next step. Okay, so that's going to be the integral of 1 minus cosine to x over 2, the whole thing squared, times cosine squared, which equivalently is 1 plus cosine to x over 2 with respect x. Okay? Well, so before we can keep moving through this one, we need to simplify the power 2 over here. So number one, okay, let me do one step at a time. So that's going to be 1 minus cosine to x, quantity squared, and 2 squared, which equals to 4. All right? And over here, everything remains the same. 1 plus, or actually, let me just write 1 plus cosine to x over 2 dx. Okay, so number one thing we can do is multiply that 4 with the 2 in the denominator, and at the same time take it outside of the integral as a 1/8. And then, well, over here, what I'm going to do is square the binomial, like we did before in the previous example, which in this case it's going to be 1 squared, which is 1, and minus 2 cosine 2x, and then from here plus cosine 2x quantity squared. Alright, that times 1 plus cosine 2x with respect x. Alright, so what are we going to do from here? Yes, this one is going to take a good minute to simplify because, well, in this case we will have to FOIL the whole thing. Alright, let's do 2 at a time. 1 times, whoops, that was too far. 1 times 1 and 1 times cosine 2x. That's going to give us the following result. That's going to be the integral of 1 plus cosine 2x, and then let's do the next 2. Negative 2 cosine 2x times 1, negative 2 cosine 2x times cosine 2x. From here, let's see, so that's negative 2 cosine 2x and minus 2 cosine squared 2x. So far so good? Alright, let's do the last distribution here. No. Cosine squared times 1, that's not going to contrast here. Yep. Cosine squared times 1, cosine squared times cosine 2x. That means plus cosine squared 2x plus cosine cubed 2x dx. Alright, so that's 1, 2, 3, 4, 5, 6 terms as expected. Okay, so let's see if we have any like terms. Do we have any like terms? Alright, let's highlight all the like terms first, and I would like to highlight the square ones. Right, that's one right here, and that's another one right here. Do we have any other like terms? The cosines, the first powers. Okay, so that's a cosine 2x minus 2 cosine 2x. Let's reduce those, and then we may start integrating these ones. Alright, so the integral of 1, okay, cosine 2x minus 2 cosine 2x, isn't that a negative cosine 2x? And then negative 2 cosine squared x minus, plus cosine squared 2x, isn't that also negative cosine squared 2x? And cosine cubed. No like terms over here. Nope, 2x. Alright. Okay, so in this case, I would like to split this into 4 integrals. And the reason is because of the powers that we have for the trigonometric functions. Well, we can integrate 1, which is x. We can integrate negative cosine 2x, which is negative 1/2 sine 2x. But what about these two? Are they straightforward? Do we have a power of sine over here that can stand for the u du part of these 3 terms? Unfortunately, it's not the case. So what we're going to do then is, whoops, the integral of 1 dx, that's the integral of dx minus the integral of cosine to x dx minus the integral of cosine squared of 2x dx plus the integral of cosine cube 2x dx. Okay, again, the first two integrals are straightforward, all right? However, I think I missed a 1/8 over here. 1/8, and then 1/8, 1/8. That can be easily fixed. All right. Well, the first two integrals, they're straightforward, but okay, let's look at this at the third integral. Any ideas on what to do for the third integral? Would the u substitution work because we have a power? We have to use the power reduction formula a second time in this case, because in this case we're lacking a factor of sign that would stand the du part of the problem, which unfortunately we don't have. And what about this last term right here, cosine cube? We're in the same situation. We don't have a factor of sign that can stand the du part. So what do we do in this one?
1 minus sine.
So in this case we need to use both guidelines, right? We need to use the guideline for the even power again, and we need to use the guideline for the odd power again. So in this case, well, that's on 1/8. And I know we can integrate these two, but let's leave this to until the end, because we're going to end up with like terms. You'll see. The integral dx minus 1/8 minus 1/8 integral of 1 plus cosine 2x over 2 plus 1/8. And I did a mistake on purpose to see if you can catch it again. What mistake did I do? Yes, Anna?
Wouldn't it be cosine of 4x?
Cosine of 4x, right? Over here. Okay, sounds good. Okay, so why is that 4x? Okay. Because every time we use the power reduction formula, yes, the power reduces, but the angle gets duplicated, right? So for example, if we had the integral of cosine squared of 5x dx, this would be equivalent to the integral of 1 plus cosine 10x over 2. So the power reduces, but the angle doubles. All right. Okay, let me erase this because this is not part of the problem. This is just to explain what happened to. But of course, how about we highlight this and write a note or an arrow right here. Okay, so let's split these two integrals. Okay, I'm going to split these two integrals, and I'm going to use the Pythagorean identity on the cosine squared. So that's a 1/8 integral dx minus 1/8 the integral of cosine 2x dx minus 1 over 16 the integral of 1 dx minus 1 over 16 integral of cosine 4x dx. Notice in this case how that third term gives rise to essentially two terms. And last, 1/8 integral of cosine squared, which is 1 minus sine squared cosine 2x dx. Okay? And from here, I think we're almost ready to integrate pretty much everything. All right? Okay, but instead, I would like to combine some of the like terms. In particular, I would like to combine this one with that one. And well, we cannot combine these two because notice the angles are not the same. If they were both 4x's or both 2x's, then we can put them together. But these are going to be two separate integrals. So that's number one thing I'm going to do. The number 2 thing I'm going to do here is to do a u substitution on the last term. That is, u equals to sine 2x du equals cosine 2x dx times 2, where cosine 2x dx equals 1/2 du. Alright? So let's add these two. So what's 1/8 minus 1/16? Isn't it like 1/16, I think? And then, well, the integral minus the integral minus 1/8, the integral of cosine 2x dx, and then no need to write this one again, minus 1/16 integral cosine 4x dx, and that's okay, 1/8 integral of 1 minus u squared times 1/2 du. But how about, well, so I don't have to write this whole thing right here. Do we all agree that this 1/8 will multiply with this 1/2 to give us 1/16? And well, I think we're ready to integrate finally. 1/16 x minus 1/16 sine 2x minus, okay, be careful here because the integral of cosine, yes, it's sine, but of 4x, that requires a factor of 1/4, and that factor of 1/4 multiplying with the 16 times 4, isn't that a 64? Sine 4x, and well, in this case we have 1/16, the integral of 1, which is u, minus 1/16, the integral of u squared, which is u cubed over 3. But that 3 multiplying with the 16, isn't it a 48? Plus c. All we do now, back substitute. 1/16x minus 1/16 sine 2x minus 1/64 sine 4x, and plus 1/16 u, which in this case u is a sine 2x, minus 1/48 sine cubed 2x plus c. Yes.
Isn't the derivative in the yellow, the derivative of sine of 2x, isn't it 1/2? Oh no, it's a derivative.
That will be the integral. Yeah. And well, yes, we're essentially done. However, did you notice something interesting here? These two cancel. And 1/16x minus 1/64 sine 4x minus 1/48 sine cubed 2x plus c. Final answer. Any questions about it? I'm going to leave everything zoomed out for a couple minutes because you need to double check something.